Yeah, that's probably it.
How did you solve that? How did you solve that?
So it's never good.
Yeah. Did you do it not? Yeah. What you said?
What are like our capstone ideas?
That is a good question. I think it'll be probably the first stuff will be sometime in June, but let me check with Matthew.
Is there like a guideline
Of like what should be in what? Yeah. So the absolute requirements are that there has to be like a substantial programming component, and you have to give a 10-minute presentation on it and write a report about it.
Okay.
Good guidelines are that it is like a coherent project that makes the other, like the report stuff easier. If you can say like, this is like the project, I did these steps and I got here. So that's kind of vague, but if you have ideas, you can bounce them and run it past me, and I can let you know if that's kind of what we have in mind or not, and we can try to figure out how to make it work.
Or is like whoever.
I'm trying to decide if it was up to the advisor or if we all approved them together last year. I'm not sure. I think we will try to come to consensus. So I think I would be very surprised if you had an idea that like Matthew loved and Vern and I hated or something. So I think you could probably talk to anyone else. All right. Morning, everybody. I feel even worse today, so see how things go today. We have a cool topic, which, how many of you have seen linear regression before? Yeah, so this is something that probably most of you haven't seen. It's closely related, slightly different tool called Logistic Regression, which shares a lot of similar ideas, but some interesting differences. So with linear regression, what we're trying to do is figure out how to predict dependent variables based on our independent variables. Okay, so the simplest model was that we assumed there was a linear relationship between those two, and we tried to find the best line that mapped the independent variables to the dependent variables, our inputs to our outputs that we're trying to predict. And we saw that with least squares we could do more than just linear models. We could do the multilinear regression. We could even have terms that were not linear as long as we were just solving for the betas that were in front of them. So on this little chart here, I have our two types of variables, coarse granularities with quantitative and categorical. So which sort of quadrants would the least squares regression that we've been talking about today? What types of data do we have as inputs, and what types of data were our outputs? Yeah, so here we had quantitative inputs and a quantitative output, right? For fitting a line, right? I don't know what kind of axis you'd have that has categories along it, or a line that goes between categories. That doesn't really make sense, right? And our outputs were also quantitative, right? So we had, we mapped income to credit score or whatever. So in general, when our output that we're matching is quantitative value, we call this regression. And today we're going to talk about what happens if our dependent variable, what we're trying to predict, is a categorical value. Okay? So here, the general term for that is classification. Okay. So today we're going to look specifically in this quadrant, and we'll kind of fill in the rest as we go through. Okay. So maybe a first attempt would be to try to use the linear regression we've looked at already to do classification. So let's say I have like one quantitative input and one categorical output with like two values. So let's say I'm trying to like predict gender based on income or something like that, or predict whether or not somebody got accepted into college based on GPA. Okay. So how might I try to use the linear regression tools that we talked about to do this? If I look at my data, maybe I have GPA on one axis, because that's pretty easy to work with. How about so for whether or not they're like admitted to college or not, how do I like graph this on an axis? We touched on this a little bit yesterday. Yeah, so maybe the easiest thing to do is to just map admitted to 1 and not admitted to 0. So the data that I'm going to have will look something like this. Right? I'll have some data points where there's low GPAs that are not admitted, maybe, and then maybe my data looks like that. Okay. Right. And so now, if the only tool I know about is linear regression, how would I predict? How could I attempt to predict whether or not somebody will get into college based on their GPA? So I can put a line through here. Maybe it looks something like this. Okay. So this gives me a fractional value, right? Between negative infinity and infinity, and I need to turn that into a yes or no answer. And so how could I do that? I need to turn this into yes or no. What's the easiest thing you can imagine?
cutoff.
Just pick a cutoff. Right? And then when you predict you are below the cutoff and on the line, then you say you're not admitted. And if you're above, then you say you're admitted. So we could use linear regression to do this, right? And it might work out okay. But there's a few issues with this. So the line doesn't really match the shape of our data very well at all, right? So it kind of seems like there's a better way of fitting. Another issue is how do we interpret the values, right? So we can compare them to the cutoff, but like a question you might ask is like, how likely are they to be admitted, right? So here, you know, if my line value is here, it doesn't really tell me anything about like the probability or anything like that. There's not a good, this can tell me the binary yes or no answer, but that's about it. So we kind of like a technique that lets us think more about like the probabilities of being in either class, right? And that matches the data a little bit together. Yeah. So the technique we're going to look at today is called logistic regression, and it works very similarly to linear regression. The difference is the shape of the thing we're fitting to our data. Okay. So with linear regression, we're fitting a line. With logistic regression, we're fitting a sigmoid or a logistic function. You might also see this called smooth step. And this is a function that has this shape. And it goes from the outputs are 0 at negative infinity and 1 at positive infinity, and it goes from one to the other. So the idea of logistic regression is we're going to fit this shape to our data. And now, because the outputs are from 0 to 1, we can interpret that as a probability. So I can still, for classification, I can still look at my cutoff and say, okay, if there's above a 50% chance of getting accepted, we'll say you're accepted. But I can also answer other questions like, if this is my GPA, what are my chances of getting accepted? So this is logistic regression. That's kind of the idea. This is a better shape for the type of analysis we're trying to do. And it's kind of closely related to linear regression. Questions so far? Okay. So I'll talk a little bit about the math. So the logistic function, or basically what we're going to say, we are going to, we'll start with the logistic function. This is the logistic function. Again, it looks like that curve there. It doesn't really look like there's any parameters in here that we can change to like affect the shape of how we fit this. Right, so depending on my data, I might want to control, and I also want to control basically the steepness when I do that. Okay? So if there's a very clear division in my data, right, I would want a really sharp division between the two classes, and if there's kind of a middle area that's like, yeah, it could go either way, right? I want like a longer transition between the two classes. Okay. So it doesn't look like there's any sort of knobs that we can tweak in this logistic function to make that work. What we're going to do is we're actually going to change what we plug into the logistic function. Okay. And that's going to allow us to control where the cutoff is, and then also how how gradual it changes. Okay. So the idea here is we're actually, yeah. E is the I don't even know what the name is. The Euler's constant, the 2.718 E of natural log thing. Yeah, I actually, Euler's constant.
I know it.
Yeah. The exponential function we're doing here. Okay. So what we're going to do, the function that we're actually going to fit, and we're going to call this probability that so this is kind of a little bit of probability notation. We're saying the probability that y is 1 given x, which usually we just write out as probability of x. So this is the curve we're fitting. The probability of being in class 1. We're going to get by taking the logistic function of a line. So just like in the linear regression, what we're solving for are these betas that are the description of a line. What we do in logistic regression is we take that line and we run it through the logistic function to smush it into that sigmoid shape. So you can think of this function as like a smush. Takes a line and it gives you back that logistic shape. Okay. So we think about this. When is this going to give us like a 50-50 probability? When would the logistic function be 0.5? So this is going to be 0.5 when x is 0. Right. So we can think of our cutoff function here as being x equals 0. So our line, basically when our line crosses 0, that's our cutoff point. Okay? And so we can control that by both the beta 0 and the beta 1. Okay? So I can move the line up and down with either the intercept or by changing the slope. And then the other thing we're controlling is how quickly my sigmoid function goes from 0 to 1. Okay. So basically, as I increase the slope of the line, the thing I'm plugging in here gets bigger faster, and so I get a sharper division. Okay. And if I make my beta 1 really small, then basically I'm going to get a slower transition. Okay. So we plot a couple different sigmoid curves. All right, so this is going to have a big beta 1, and this one will have a small beta 1. Okay. And then beta 0, if I change that, it'll adjust the shift. All right. So this is a pretty nice function for what we're doing, as long as our data has kind of a nice, it shifts from one class to another. What kind of data or what kind of like data distribution would this not work at well for it like at all?
If you had two or more, or sorry, more than two states, I feel.
So more than two, it gets trickier. If I have two, the way, kind of the shape of my data can also make logistic regression really bad. So let's imagine my data set looks like this. Right. I have two classes. There's a cutoff between them, but there's actually two cutoffs between them, right? So, you know, probably what would happen is I would end up fitting something that is like flat and basically never predicts anything to be up here, because otherwise, like, I'm going to get all these ones wrong. Right? So, in this case, right, the way my data is shaped, there is not, this relationship just doesn't exist between my variables. So, logistic regression is not going to give me anything useful. Any questions about the main idea here? We'll talk about two kind of related functions that are occasionally useful. If we take the inverse of this, we get so basically, if we invert this to get rid of the logistic over here and get a line on the right, we get this expression here on the right. So it's log p of 1 minus p. This p over 1 minus p has a name. These are called the odds. And so probability goes from 0 to 1. What does the range of the odds look like? If I have a probability of like almost 0, what am I going to get here? I get like 0. If I have a probability really close to 1, this thing is going to get really, really huge. So the odds go from like 0 to infinity. So this is another way of thinking about probability. Just kind of like rescaling the probability in a different way. We're not going to use this too much, but you may see it. And then this function, this is called the Logit Function, which is the inverse of the logistic function. So you'll see this as well in a couple places. Okay. These are kind of interesting to us when we want to figure out basically what inputs would give me a particular chance of something happening. So if I want to know basically what x is going to give me a 25% chance of being in group 1, then I set this equal to 0.25, and I have to invert this to solve for x. Right? So the Logit function could be pretty helpful there. So we'll see examples of that, but this helps us solve for x given a probability that we know. Okay. Right. That's kind of the main idea. We're fitting a different shape. We have the same parameters. They mean the same things they did before, but we add this extra step of running everything through the logistic function to smush it, and that gives us a nice delineation between our two classes. Right? We can use a threshold to to assign a class to an input, or we can look at the probability and get a more nuanced result out of our fit. Any other questions about that? Okay, so let's go ahead and take a look at some code. So this is our first classification problem. Here we're predicting a categorical variable based on our inputs. For logistic regression, our inputs need to be quantitative. Yeah, we'll talk about, we'll look at logistic regression today. So one of the things, well, we're interested, once we've developed one of these models, we need to evaluate to see how good it is, right? So when we were talking about linear least squares regression, how did we kind of determine how good our model was at fitting the data? The R squared value told us how well did it match the data. Okay. So a useful thing for classification problems is it's called the confusion matrix. And basically what we do here is we just make a table of the predicted and actual values for the data that we're testing with. Okay. And things along the diagonal are good, right? It means the predicted class and the actual class are the same, and things on the off diagonal are bad, right? So we can kind of look at this to see how we're doing. So in this case, when we predicted a cat, most of the time it was a cat. We got confused with dogs a little bit, but our cat predictions were pretty good. Our rabbit predictions were great. We only got one wrong when we predicted rabbit, but our dog predictions were pretty bad. And so less than half the time that we predicted a dog did we actually have a dog. Also, if we look at kind of by column, we can see that our method has a hard time telling dogs and cats apart. There's a lot of confusion here, but we're really good at telling rabbits apart from the other animals. So that's how we can evaluate a classification method. We'll look at the confusion matrices for the predictions that we make. Okay. So yeah, this is the ugly math. So this is kind of the expanded version where we plugged that line equation into everything else. This is probably the more useful way of thinking about it. So it's the logistic function applied to this line. So we're taking a line and we're squishing it. Yeah. This is kind of a useful thing we'll do a lot. If we have a probability that we're trying to figure out where is the cutoff, or where does that probability meet, where does our curve cross some particular horizontal line, we use the Logit function, which is the inverse of the logistic function, and then we can solve for the x that we're interested in. Okay. And again, this p over 1 minus p is called the odds. It's just kind of like a scaled probability that goes from 0 to infinity. So here we'll look at just the graphs of a couple of these things. So the logistic function, the way we get that is 1 over 1 plus. So actually, there's two different ways of writing out the logistic function. They're algebraically the same. But this way we only have to compute one e to the x, which is expensive. So if we're computing stuff, this might be more efficient. So when we're working with e, usually we work with the x function. So most like programming languages have, with their sine and cosine, they have an x function that takes e to a power. So this is a logistic function, right? It crosses through 0.5 at 0, and smoothly goes from 0 to 1. The odds, again, is p over 1 minus p. The Logit function is the inverse of the logistic function, which is the log of the odds is one way of writing it, or it's just log of p over 1 minus p. And so these ones only make sense between 0 and 1, right? So since odds is based on probability, it doesn't make sense to look at the odds out of anything beside, outside the range of 0 to 1. The Logit function is the inverse of the logistic function, so basically there's no values outside of 0 and 1 to invert. And so these ones only make sense between 0 and 1. Okay. And so yeah, the odds go to 0 as the probability goes to 0, and they go to infinity as it goes to 1. And the Logit function is basically the logistic function kind of turned on its side. So let's take a look at an example here. So we'll look at, basically we have a bunch of data where our independent variables are the number of hours that students spent studying. And the thing we're trying to predict is whether or not somebody would pass the exam. So the data points that we have are study time and then whether or not they passed. Okay. So here's just the data that we have here. We just have amount of studying they did and whether or not they passed. And then this is what the data looks like. Okay. So we could fit a line through this, but like it wouldn't fit very well. But I think you can see the logistic function kind of seems like it will fit this better. Because over here, if you don't study, you're probably not going to pass. And then you can expect, like, as you study more in this range, you up your chances, and then beyond here, you're probably going to pass. So that's the idea. So we want to figure out the probability of passing as a function of how much you studied. So we're going to do logistic regression. So here we'll use the stats models. It looks very similar to the least squares that we're doing, except that we use the logistic function instead of the OLS function. And the output that we get also looks pretty similar. An interesting, so linear regression, the least squares, is really, really efficient, and we can solve it basically kind of in one shot. Logistic regression, there's not a closed form answer for what the betas are. So if you remember for the least squares, there was that formula for the beta 0 and beta 1 that was like the x minus mean x times y minus mean y, all that stuff. There is nothing like that for logistic regression because the logistic function, the way that it squishes stuff, there's no way to like solve directly for what we want. So the way that we actually compute the betas is we make a guess, and then we iteratively improve those guesses. So we kind of measure the error, and then we adjust the betas to reduce that error, and we do that a bunch of little times. So in this case, it took seven iterations for the solver to figure out what the betas were. Whereas with least squares, it would happen just immediately. So this is more computationally expensive than the least squares that we saw. Okay. So when we get out, we get a pseudo r squared. And so we don't measure exactly the same thing as we did for our least squares regression, but this is kind of a comparable value. So we see that we have a r squared of 0.42, which if we look at the data, there's no way that we can fit a sigmoid that's going to hit all the data. So we shouldn't expect to get like 0.99 r squared or anything. And then we get the values for the intercept and the coefficient. So this is the beta 0 and beta 1. Okay, so it looks like each hour of studying gives you a 1.5 unit increase along the line towards passing. If we look at the p-values, the p-values here are both not as low as we saw for a lot of the linear regression. So these are p-value of like 2%, which says that maybe this isn't the most predictive model. And if we plot the line we saw, so here we're going to plot the line, we're going to compute the logistic of beta 0 plus beta 1 times x. And this is the curve that we look like. So in this case, our beta 1 was, I guess, relatively small, which is what's giving us this smooth, like long transition region. And that's because the data doesn't give us a clear-cut, transition. So now that we have this curve, we can use it to talk about the probability of passing as a function of how much you studied. Okay. So if you studied 2 hours, you plug in 2 for your x using the parameters you solve for, and so it's like 2 hours of studying gives you a 25% chance of passing. So not great. There's also this predict function, which is a little bit cumbersome to use because you have to, you need like a data frame or a series for it to predict with. Yeah.
What exactly is the coefficient saying here? I have a tougher time wrapping my head around that regression.
Yeah. So what we're doing is we're fitting a line, and then we're smushing it with the sigmoid function.
Right.
So the beta 1 is the steepness of that line, and that tells us basically the sharpness of it's going to be the steepness of the transition. And then the beta 0 is going to control the where the transition occurs. So let's see. So it's not like a direct thing. So my intercept is at -4. That doesn't mean that -4 hours gives you a 50-50 chance of studying. It's like kind of an indirect thing, but those are what those values control. Yeah, other questions? So yeah, we can use the predict function to predict this as well. So another interesting thing we might want to do is figure out like when do I have the 50-50 shot of passing? How much should I study if I want to, live dangerously? And so basically, we put the 0.5 in over here, and we solve for x. Right? So we take the logit of how much of probability of passing, and then we just solve for x. So subtract out the intercept, divide by x. And it looks like after about 3 hours of studying, I need a 50-50 shot. Let's see if I wanted to be really confident. It looks like I need 4 hours. And so an hour is only going to give me, or an hour and a half is only going to give me a 10% chance of passing. We can look kind of visually to see how we do here. To quantify how good we're doing, we can take a look at the confusion matrix. So this crosstab function we can use to make a confusion matrix. So we're going to, for all of our data, we're going to run it through our model and see whether it says they should have passed based on the number of hours they studied. So here we're putting our cutoff at 0.5. We're saying, is the output of this more than 50% chance of passing? And then we're going to make a little table showing what happened. So here's our predictions in columns. And then here's the actual values. So it looks like 80% of the time we predicted correctly. And then 20% of the time we predicted wrong. And our errors were kind of symmetric. Right? So we predicted that somebody that studied a lot. So we mispredicted somebody who studied a lot and failed as often as we mispredicted somebody that didn't study that much and passed. So seems like a pretty good model for this case. Right. Any questions on just like seeing this in practice? Okay. So we'll take a look at a more complicated scenario here, which is graduate school admission. But now we have a few more factors. So we have their GRE scores, their GPA, and the prestige of their undergrad university, which I don't know exactly where they came from, but they have somehow assigned a number to it. Okay. So if we look at the data we have 400 samples, and we had, whether they're admitted, GRE, GPA, prestige. So this seems like a pretty bad GRE score. This person, I assume one is high prestige. They aced their GRE and had a 4.0, so of course they got in. So if we look at description of our data, and we have, looks like only 31% of students were admitted, which seems kind of low to me. I don't know what kind of grad school they're looking at, but only 31% admittance rate. GRE mean looks like it's pretty good. GPAs are pretty high. Prestige, I don't know what that means. But it's a number between 1 and 4. And if we look at the scatter matrix, it's kind of hard to see any sort of meaningful relationships here. Does anything jump out at anybody? Yep. And admittance and GPA, or admittance and GRE, this looks like it's not that helpful. We have lots of dots kind of distributed the same for GPA and admittance. Prestige, you can't tell because all the dots are aligned to each other. But it does appear that at least one person that went to Harvard didn't get admitted, and at least one person that went to, name a bad school did get in. So that's kind of all we can tell. Okay, so the GRE is designed to identify whether or not people will be successful in graduate school. So we might assume that your GRE scores would tell you whether or not you're going to get admitted. So we'll try to do a logistic regression. We'll just assume that it only depends on your GRE score. And see what we get. So our formula is just going to be logistic admission based on GRE. Let's run it. And our pseudo R squared is 0.02. So that seems pretty bad. Right. Our P's our p-values are non-zero, so that seems to me that all the terms are important. But the R squared tells us that the kind of the predictive power of this doesn't seem like to be very good. So if we plot this, what are our predictions going to be if we use this model? Well, so where's the 0.5 line?
Looks like nobody gets in.
Nobody gets in. So this model says that every single applicant is rejected. Okay. So if we look at our crosstabs, we see the only values that we predicted were false, that you didn't get in. And we were wrong about a third of the time. So 30% of people actually did get admitted. We predicted that nobody got admitted. So this doesn't appear to be a very useful model. Okay. So one of the reasons that the MSD program has stopped requiring the GREs for domestic applicants is clearly it's not a good indicator. Or on its own, it's not a good indicator, let's say. Okay. So let's say GPA, we want to include that as well. Okay. So just like with the least squares, we can add sort of more terms as long as the betas are just in front. We can do the same thing here. So we're going to add another beta for the GPA, add another term here, and go ahead and fit that. Our R squared jumped all the way to 0.03. So still not very predictive, but an improvement. Okay. Our p-values are still pretty good. It looks like, from the looks of this, GRE might be a better indicator than GPA. Which actually, we'll take a look at that after this. So if we do a confusion matrix here, so we're going to predict using this new model, and then make our confusion matrix. We see that now we are predicting a few people will be admitted. Unfortunately, less than half of those that we predicted to be admitted actually were. Okay? And we're still about almost a third of the time predicting that people will not be admitted when they in fact were. So still not a very good model. Let's take a look at just what a GPA model would look like. So it looks like we got an R squared of 0.026 compared with 0.027 for the GRE. So it looks like GRE is a slightly better predictor than our GPA, which is a little surprising to me. We'll go ahead and plot this. So again, our GPA model looks very similar to our GRE model, where we don't predict very many people are going to get in. We look at our confusion matrix. Again, based on GPA alone, we're predicting that nobody will be admitted. Right. So, we have one more term to consider. Of course, the prestige. You always have to consider the prestige. What we're going to look at here is trying to understand kind of why these aren't great models. So we're going to plot the GPA and the GRE, and we're going to color the dots based on whether or not people are admitted. Okay. And then we're also going to plot the 0.5 line for the combined model. Okay, so if we think about the so now, if we think in 3D, we don't really have we no longer have a line with a curve. We have actually a plane, and then there's some surface that has this step. Okay? And so basically what we're trying to do is we're trying to orient and slide that surface into the right spot. Okay? And so what we're drawing is we're drawing the cutoff line of that surface, kind of projected onto the ground, if that makes sense. Okay? So what we have here is the 2D space of our data, and then this is where the cutoff is between reject and accept. So if we look here, the way we're getting that is we're doing the logit of 0.5, so we're solving for the inputs that give us a 50% chance of being accepted. So that's what we're plotting here. And yeah, so you can see, and this is the group of people that we said should be accepted according to our model. Doesn't look very good, but if you look at the data, how are you going to do better? Where are you going to put this that actually separates the blue and the red dots? They are not separated in this view. So, looks like we're going to be kind of out of luck here. Okay. So the last thing we'll look at is adding in the prestige. So if we look at the admittance rate based on prestige, it looks like the lower prestige scores had a slightly higher acceptance rate. So prestige of 1 was more than 50-50, and prestige of 3 and 4 was way less. So maybe by adding prestige, that'll help us out. You could imagine that the GPA alone doesn't mean much, but the GPA at the school you are at could mean a lot more. Maybe. And let's add a third term to our model. And our R squared goes all the way up to 0.08. So much better than before and still really bad. Our p-values look like they're reasonably good. Our predictions are a little bit better. But so more than half the time we predict true, we're right. And 2/3 of the time when we predict false, we're right. But we're still missing an awful lot of people that were actually admitted, and we're saying that they shouldn't be, basically. So better, but still not a very good model. Okay. So basically, for the students that were not admitted, we're pretty good at nailing that. But we don't need a sophisticated model to be pretty good at classifying the students that weren't admitted. Or if we just guessed that nobody would be admitted, we're hitting 70%. So, you know, the fact that we're doing good here doesn't mean a whole lot. The challenging part is predicting the students that were admitted because it's a smaller number, and we're not doing a very good job there. Yeah.
So why were the first couple models, why are they so bad? It feels like the curve would figure out a way to interpret something more correctly.
Well, there's just a bunch more points down here. And so just, if I curve up, then I'm going to be wrong for all these points down here. Right? And that error is going to pull it back down as it's solving. So there's, yeah, there's so many points down here that basically these ones up here don't outweigh it. Yeah. So just a little curious, let's try one more model where we let's see if my prediction about GPA times prestige mattering. So some sort of combination between the GPA and the quality of the school you were at, although the fact that the prestige is decreasing, maybe, let's do, I don't know if this is going to work or not. Yeah. Okay, so let's look at that. It looks like it made basically no improvement. Oh, and I crashed the solver. So these nans here mean that something went really wrong in the solver. So I guess this was not a good approach. Yeah.
Did you happen to know if this is real data?
I'm not sure. It came from. So the blog post that it came from is here. So I wanted to look at a couple other examples. So one thing we'll look at data where we have two classes, but they're not divided by a nice line. So we'll go. So we're going to have x's that are just evenly spaced from 0 to 10. And then my y value is going to be basically, we're going to do we're going to see if they're close to 5. Okay, so my y values are going to be like 0, and then near 5 they're going to be 1, and then they're going to spread out further away. Does that make sense? Yeah. So this is our data, and so we're just going to pick points like this, okay. And then let's make a data frame. There you go. Okay. And so we have our data as a data frame. Let's go ahead and we'll just change. We'll map the Y column to numbers. So now we have okay, let's do it. Cool. So let's try to do a logistic regression here. I'm just going to look at x as a function of y. Look at the summary. There we go. Okay. So if we're looking here, this is even worse than the GPA one. Let's take a look at, plot this and take a look at what it looks like. We're going to plot our x's and y's. And so this is the curve that we came up with, which obviously does not represent the data at all. This one actually goes down, which we haven't seen before. The idea is what is making that happen? Why it would go down? And so if I looked at the parameters that actually got fit, how could I tell that it's going to go down? Which of these parameters tells me that it's actually going to go down? Yeah, so my x coefficient is negative, right? Which means that the line that I'm squishing is actually pointing down. So I'm actually going to go from high to low when I fit my sigmoid. Yeah?
What's a good pseudo R squared? Like, what are you hoping for with this? It's not going to necessarily do a great job ever.
Yeah. So what we saw here, this was the hours versus studying. This was like 0.4. So it kind of depends on your data, but like that seems reasonably okay here. Yeah. So let's try another example where where it works really well, and we can kind of see what that looks like. So now we'll just do, instead of now we'll do we'll just look at we'll switch over at 5. Okay. Do you guys use this the ternary operator before? Have you seen that?
Yes, it doesn't
Like a-
work under Python.
Oh, it doesn't? No. Okay. Good to know. So we'll run through the same stuff. Make a data frame out of it. Okay. And if we fit this one, that's a surprise to me.
The V1 value is going to be infinity.
Because it's such a sharp. Yeah, but it should, I would think the numerics would work out because I don't know points. We'll just cut down the number of points. Yeah, I wouldn't think it would be sensitive for that. Okay. So here I'm getting a pseudo R squared of 0.99 because there is a really sharp and perfect cutoff between these. So if we go ahead and plot that. Okay. Yeah, I mean, that one we nailed. Okay. So the fact that it crashed solving makes me a little bit irritated because it seems like it should be able to handle that. But it gives you an indication how much harder of a problem this is to solve computationally than the ordinary least squares, which is like, that never screws up. Like, that's always works. It might give you a bad answer, but it always gives you an answer fast. So I'm not sure how we crash this here. But you know, for this particular data where there is a exact cutoff, like we nailed it with our logistic regression. Okay, so just as a kind of a warm up to what we'll talk about next week, how do we handle something like this? Any ideas on stuff we could do? Like throw out crazy ideas.
Layers of indirection. Split it up.
We could do have multiple layers of like different models and combine them. That is closely related to something we will do a little bit later. A name for that is neural networks. So yeah, we'll do something like that.
Try to just get more data.
I don't know that would, like, if I add more points here, that's not going to make this model any
I
better.
don't mean like bigger n, I mean like something other than GPH and the other.
Well, so in this case, this is the case where we have two groups, but like there's not it doesn't go from one to the other, it like goes back. Yeah, so I could try to fit a different shape, right? So maybe this one actually seems like it might be described by like two sigmoids or something. Like, so I add two of these together and then like scale them somehow. Maybe that would work. But yeah, try to fit a different shape. Although the shape here, I don't know what shape this is, and a lot of time we have kind of no idea what a reasonable shape would be. Are there ideas? So we don't. Let's say we're not going to fit any lines here at all. How else could we approach this problem? So let's think about the problem we're trying to solve, which is I give you an x, and you're supposed to tell me whether I should output 0 or 1. Right? So if I give you an x here, what should you output? And if I give you an x here, if I give you an x here, I don't know, maybe not a good answer. Yeah. So the way that we have been approaching this is like, okay, we're fitting a line and then we're seeing what side of the line we're on. Fitting a line here seems really hard. How else could we decide, whether to output 0 or 1?
Setting like linear cutoffs. Range.
So one way is I could split up the range if I like knew how to do that. Yep, so that's a possibility. It might be hard to figure out where to put those, but yeah, we could do that. How did you, without knowing where this data came from, how did you know that when I pointed there that you should probably output 0? You look at the ones that are nearby, and then you kind of let them tell you how you should vote on this. So that's actually the next technique we're going to start talking about, which is k-nearest neighbors. And that is we call it like a non-parametric model. We're not trying to fit anything. We're just looking at the data nearby, and we're going to vote. So that's kind of a teaser for next week. So that's the next classification tool. Okay. Any other questions? All right. Go ahead. Enjoy your long weekend, even though it's from our perspective, it's the same as normal weekend. Yeah, Varun should be back to teaching on Tuesday. Sounds like he got sick traveling, which I can relate to. So enjoy your weekend, and we'll talk about KNN on Tuesday.
Question. Part 2, task 3.